So, we started with the propositional logic, where the building blocks are the propositions, the sentences without any connectives there, and the connectives only help us to break down the propositions into smaller parts. Then the smaller parts are being taken to true or false by semantics, 1 or 0, and then we have come across many proof methods also. Okay. So, one proof method is the axiomatic approach, which is the propositional calculus. Next we considered resolution also we have considered, and then the analytic tabula, right. So, from the semantics itself we got two methods which are informal still. It could be made formal, but we did not choose to make it formal. One was calculation, another was informal proofs, right. So, then let us consider another argument, see what happens. Okay. So, this argument you accept to be true, right. Now, let us symbolize it in propositional logic, PL. So, for symbolization, first principle is find the connectives or connective looking like words, and then break it into smaller units. Now, there is no connective in the first sentence, okay. There is no connective in the second sentence, there is no connective in the third sentence, only that therefore, but that is for the consequence relation. If you assume these two are premises, the next sentence that follows is a conclusion. This is not implies, it is not a sentence. Kalidasa is not a sentence. In a propositional logic, the building blocks are the propositions. Kalidasa is not a proposition.
You are converting English to a proposition, right?
Yes, tell Kalidasa is not a proposition, it is a name. It refers to one person. It cannot be true or false, right?
Kalidasa, the person
was a person, that will be a sentence. So, Kalidasa was a poet, that will be another person, that will be another sentence. But then why is it implies? Even if Kalidasa could have been one animal, he would have been also a poet. If it is not a person, still it is a poet. The sentence does not say, there is an implies in it. Do you see the problem? Okay. So, at best what we can do is, I can write P for this. Kalidasa was a poet, I can write P, it itself is a sentence, right. There is no connective in it according to propositional logic. So, I have to denote it as P, some sentence. Then all poets are Y similarly, another sentence Q. Forgetting this, therefore, the other sentence is R, right. Now, the whole consequence we can write as P, Q as premises and R as a conclusion. Of course, we do not know whether this consequence is correct or not, right. So, okay, it is a consequence, the whole thing is translated to a consequence. Now, in propositional logic this will not be valid consequence, fine, because you can make one interpretation which makes this true, but R false. Just take P equal to 1, Q equal to 1, R equal to 0, they are now independent units, independent propositions. That is why you are trying to do it some other way, right. So, you are going a step ahead, that they will become independent propositions and they are not really independent, somehow they are depending, right. That is why the conclusion holds true. So, the question is how are they depending, that is what we want to find out. Okay. So, let us take the first sentence, Kalidasa was a poet. It looks like there can be other poets, Omar Khayyam was a poet, right. So, you can take many more. So, that means this poet being a poet is a property. The sentence asserts that being a poet is correctly applied to Kalidasa. That is the information we get from the first sentence, right. So, being a poet or is a poet, let us say, is a poet becomes a predicate now, it is a property or a relation. That property holds for Kalidasa, right. That may hold for Omar Khayyam, that may not hold for Arindam Singh, right. Is it okay? So, it can be true or it can be false. One predicate can assert truth or falsity about some object, that is what we see here. Okay. So, that means we should have predicates like is a poet. Similarly, is wise, that is also another predicate, fine. They are unary predicates, in the sense one person to one person only it applies, it has only one argument. Something or somebody is a poet, right, but you say X likes Y, so that likes become a binary predicate, it is not unary now, right. So, 2 lies between 1 and 3, that becomes a ternary predicate, there are 3 arguments here, something lies between 2 other things. So, there are really 3 arguments involved, it may be true, it may be false, okay, when applied to some particular objects. So, predicates can be there with different number of arguments, that is possible, we need that. Second thing here is, in the first sentence Kalidasa is a name, it refers to some object, as we understand it refers to some person here, right. Okay. So, it is a name, so you should have some names, say proper names, we just call them names, individual constants, they should also be there, right. So, we need names. Then what else we need? So, now when you look at third sentence, Kalidasa was wise, this also requires the same thing, is wise is one property or a predicate, it is a unary predicate. Then Kalidasa is a name, that is accounted for. What about the second sentence? Already we have told is a poet is a predicate, is wise is a predicate, right. So, this sentence connects to predicates now, it is not a name and a predicate, whether a predicate holds for a name or not, this sentence does not say that, it connects now two predicates and it says in a particular way, it does not say all wise persons are poets, right, it says something in a particular way, all poets are wise. So, how do we translate it? See, we think that predicates will be applicable to some object, one particular thing, it has an argument. Now, if you say all poets are, but the predicate cannot imply, predicate itself is not a sentence, right. Suppose is a poet, it has a vacancy. So, one vacancy we know because it is a unary predicate. Now, once that vacancy is filled in by Kalidasa, it becomes a sentence, right. Now, here is a poet, there is a vacancy, okay, and is wise, there is also another vacancy. So, sentences will become once that vacancy is filled in. Suppose you write it at some gap is there, like X is a poet. Now, still we think of this as a gap, it has not been filled in yet, okay. We are just giving it some name, it is not a name really, pseudonym, it is a gap, we remember it is a gap. Similarly, I can write Y is wise, there is still a gap, but this gap and this gap are different, they have different names, they need not be same. Unless this sentence is there, I cannot say same X can become poet and wise, they may be different completely, right. So, this particular thing which is a gap, but the gap has a name, right, they are named gaps, we will call them as variables, just with our usual mathematical procedures, right. So, we will call this X as a variable, they are sometimes called individual variables, So, we need variables which are just named gaps. Once they are filled in by some particular objects, we get a sentence in a predicate. Okay. Now, then how do we write this sentence? It says some implication you are telling, right. So, you say if X is a poet, then X is wise. Now, we do not say Y here, right. It is the same person you want to become wise, same poet should be taken as wise. Now, but this is not a sentence yet, because we do not know what X is, what X stands for even. It is a real number? No. All possible names. So, you have to write something like for each X, if X is a poet, then X is wise. It looks all right now. That is what we mean by all poets are wise. You take any person or anyone, now in the poet itself person is included, that is our interpretation. So, you take any one or any object, if it is a poet, then it has to be wise. That is what the sentence says. Is that clear? Now, look at this, we have variables, we have predicates, variables, predicates, something else we name, right. So, these are called the quantifiers. For each X is a quantifier for each. It is a quantifier for each. There is another quantifier, it says for which X we are really talking about, for all. So, it quantifies over that variable. It can become something like some poets are eccentric. Okay. So, there is another quantifier there, it is not for each, for some, or there exists at least one, or there is, right. So, you may need that also, there exists. So, this is another type of quantifier, or there exists at least one. Okay. We will not always say at least one, just say there exists or there is for some, it has the same meaning. Even for each also we sometimes say for every, for all, but those two words really are ambiguous, sometimes it creates problem. You say for all men X, X has only 2 legs, right. So, it is all men do not have 2 legs. No? If you take all men together, count the legs, it is not 2 legs. So, it gives rise to that ambiguity, all applied to everything as a whole or individual persons in that, for each clarifies it. Okay. Sometimes every also becomes ambiguous like that. So, each is a better word. Of course, each can also you can interpret in ambiguous ways, usually it does not, each means one particular person, and then look at everyone. Okay. So, these are the two quantifiers we will be using, for each and there exists. So, these are the quantifiers we need. Fine. So, see how many things we are going to need slowly. We will take another sentence and see what happens. Say Kalidasa was liked by the king of Bhoj. Now, how do we symbolize this, or how do we translate into our pseudo sentence like this? So, Kalidasa is a name that we know, is liked by, it is a predicate. What is the argument? Number of arguments? Binary, right? There are 2 arguments, one person liked by another person, X liked by Y. So, there are 2 arguments there. Okay. Then next, is it a name? King of Bhoj is a name. Then king of Persia, that will be a different name, but they have something. If you want to express that there is something, common in between them, you have to really go a bit deeper, right. You can take king of Woes as a name, does not matter, it refers to a person and get away with it, right, that is okay. Suppose there is another sentence where king of Persia is also involved, and now you say king of Woes is not the same as the king of Persia, right. Suppose you write another sentence. Okay. Let us write this sentence. Now then I will say we want king, right, not sultan, they are same thing, let us take king. Now we say king of Woes was not the same person as the king of Nishapur. Now you can take king of Woes as one name, does not matter, it is a name, say A is not equal to B, that also you can do. But say you want to go deeper, you want to say king of, I want to express this king of, it is missing that king of thing, right. You may need here a sentence that king is required, not the jack, right. So then what should you do? Is it a predicate? Is it a predicate? See, suppose it is a predicate, why, what is, we have to say why it is wrong. Suppose you say it is a predicate, king of something. Now you see, for example, it is a unary predicate. So let us see one unary predicate here, is a poet. So when you say X is a poet and you fill up that X with some particular constant, or instead of fill up you say X becomes bound to some constant, say Kalidasa, you get Kalidasa is a poet, which is a sentence, right. Now say king of X, there is a gap there. Now suppose X is bound to Woes, Woes is an object, then king of Woes should be a sentence, it is not, it is again another person, right. See the problem. So it is not a predicate, it is a different entity altogether, because once that gap is filled in, you are getting an object, not a sentence. So there is the difference. So we will call them as definite descriptions, that describing, they are describing a person definitely through a property, but that property really gives the description of the person, that person is uniquely determined by it, right. That is why they are called definite descriptions. Okay. Sometimes definite descriptions can look like definite descriptions, but they can be vacuous, right, like the present king of France, it is a definite description, but it gives nothing, there is nobody which is a king of France now, right, but it is a definite description, it describes something. So these describe, these things which describe a person, right, when you fill in the gap you get an object or a name. The definite descriptions can be described through something having a gap, that is what we find out, like king of. Okay. So we will give them again through the function symbols. So it is something like your function, say f of x. So when x is filled in by some 1, you get another value of that, say 5, right. Suppose it is square function, so you fill up f of x, x is filled by 2, you get 4, again numbers, right. So we will write them as function symbols, they are not functions, because nothing is specified, no domain, no range, right. So we will just tell them function symbols, just like our predicates. Similarly, if you think of function symbols as functions, you can think of predicates as relations, they relate to objects, right, that is why they are predicates. So we need here function symbols. Okay. Now, let us see another thing. You say Kalidasa was liked by the king of Bhoj. This is liked by, x is liked by y, it is a binary predicate. Now, how do you interpret this liked by? It depends on our usual convention in English, liking means what, right. But when you come to a formal language, we will have nothing there, we will interpret maybe some other way or explicitly tell liking means these ordered pairs are true, okay. But we will have to interpret them specifically. We cannot use our ordinary common sense of liking or hating or something, okay. But they have to be interpreted in some way or other. Okay. Now, when you come to the last sentence, king of Bhoj was not the same person as the king of Nishapur. The same as cannot be interpreted as anything else, right, otherwise there will be problem. It has to be that equal to, same as means equal to, right. So, same as has to be interpreted in one particular way as regard to other predicates, that is how we are specifying it now itself. We have freedom to interpret any other way also, just like any other binary predicate, but it will never give the sense. Liked by can be interpreted different ways, right. For example, you say author of a book, okay. Now, author of means what? Who has actually written it or whose name appears on the printed book, right. So, you have ways of interpreting it, whatever way you like father of, who is physical father or social father, he might have adopted, right. So, that way we can think of interpreting it, but the same as we do not want to interpret any other way, it is a particular one interpretation, right. So, we will preserve a different symbol for this, we will call it equality predicate, which is binary and which is has to be interpreted that way only. So, let us fix it, identity predicate or equality predicate. See, all these things we need now to express a simple argument like this, okay, and some more particularly we want also something more. So, we have to get together, we have to make them at a place and see what are our requirements, what are the things we need. Moreover, we need also propositional logic to be inside this logic, it is a new logic we are forming, right. So, it should be an extension of the propositional logic, that truth, falsity, connectives they also should be there, otherwise we will be in problem, right. We cannot give this P and Q implies R and so on, right. So, let us start with that. Then our alphabet of this called first order logic, or we will write as FL. So, this will have now many types of symbols, all these types of symbols, we will reserve some symbols for them. So, first we have variables, which are the individual variables, say we will put as x0, x1, x2 and so on. It is an infinite list, denumerable set of symbols. Then we will have what? Predicates. So, we will write that Pij, why 2 I and j's are there, because we also want to say what is its arity, how many arguments it can take, right. So, the superscript j will tell us how many arguments it can take, like suppose you want to symbolize is liked by, so that will be one predicate with superscript 2, okay. Is a poet will be one predicate written as a predicate p something, say 100, but superscript will be 1, it will tell how many arguments are there, right. Next we will have the function symbols. So, similarly we will put Fij. So, it is the set of, so that the such that symbol will be meaningful, okay. Set of variables, set of predicates, set of function symbols. Next we need something else, say quantifiers. So, we have only 2 quantifiers for all there is. I read it for all now, because you can remember this. It is just A written different way, and this exists E written different way. Okay. So, we will read them as for each and there exists later. Then we have the connectives, not, and, or, implies, biconditional, and we have the propositional constants as earlier, top and bottom. Okay. Anything else we need? Well, no, they are different, right? They are only named gaps for the objects, and these propositional variables are sentences, really propositions. So, propositional variables are there inside it. J stands for number of arguments. Suppose there is 0 argument. So, we will put a convention that they are the propositional variables. Right? If there is one argument, you substitute something in that place, it becomes a sentence. So, there is no argument required for it to become a sentence. Right? That is the sense we are using 0 there. So, p I zeros are the propositional variables. Okay? No argument is required there to become a sentence, 0. So, we will make it a convention to take them as the propositional variables instead of taking another class. Now, function symbols, put j equal to 0. So, again in function symbols, if there is one argument, one vacancy is there, you fill up with a constant or a name that gives you another name, right, definite description. So, here it says nothing is required to fill in, so that it becomes a name, it is a name by itself, right. So, they are the constants. Function symbols with j equal to 0 are called as constants, they are called individual constants. They give you individual things, objects, like your individual variables. So, they will be different from propositional constants, they are propositions, but individual constants are objects. Okay. One more crucial thing for unique parsing, punctuation marks, right, punctuation marks, parenthesis, you need brackets, right. So, let us write punctuation. So, we will have now 3 punctuation marks, 1 comma, sometimes f of there are 2 things, so we will write comma, right, p of 2 things we will write a comma, and then we have the parenthesis, usual parenthesis. So, 3 punctuation marks. Okay. So, this comma can really be removed. So, sometimes we will not have the comma, even we will read it through, but that requires some eye to read it, some trained eyes. Fine. Now, you have to form the language. So, as you see, it will be a strictly typed language, so many types of objects are there, just like your Sanskrit or something. So, when you have this kind of verb or this kind of vibhakti, verb will take this form, nothing else is allowed. So, that way it will go, like if you have subscript superscript of p as 1, it will take only one argument, you cannot write 2. Okay. So, similar things will be preserved. Fine. So, we have to slowly develop our language from this. First thing we have to develop is this kind of things, definite descriptions, okay, because functions are there. So, you can have a function inside a function also as an argument of another function, right. Suppose I want to express mother of brother of Rajiv, right. So, how do you express? Mother of is one function, brother of is another function, okay. Then you have to do mother of brother of somebody. So, a function can take another function as an argument also. It can have indefinite length, finite, but how many we do not know, right. So, first we have to define that recursively, then we go for the formulas or sentences in our language, fine. So, those are called the terms, we will not call them definite descriptions, their meaning will be definite descriptions. We are starting from the meaning itself, how to symbolize the sentences. So, in our language there is nothing, no definite description, no sentences, there are only symbols, right, expressions, strings of symbols defined over this union of these sets which we have taken. So, our alphabet is the union of all these, how many? 7 sets, right, 7 sets. Then from over that alphabet we take any string, that is an expression. Now, this FL expression we have to now tell which are really okay for us, which are not okay for us, right. We have to define that, that is how we will be defining our language. Just the same way as propositional logic, connectives are there, propositions are there, punctuation mark is there, but everything is not a proposition, only some certain way if it is formed it is a proposition. Similarly, we have to define here, fine. So, first we will define those which are parallel to the definite descriptions, which will be used as definite descriptions or which will translate the definite descriptions, they are called the terms. So, we define first terms, we can just give its grammar, what is a term, right. So, let us write a term can be a variable, any variable you can take, or it can be any individual constant that will look like this with 0 on the top, or it can be any function symbol with some arguments, right. So, with some arguments means we have to again say inside that what are allowed, here is the recursion, inside that again some function symbols can be allowed, right. So, we will just write t. So, here t is taken j times, is it okay. So, it is not the same t as earlier with our grammar convention, it can be different, they are just term, generic term t, okay. Or you may write t1 to tj, where t1 to tj are terms, again some terms, is it clear. So, if you break it into rules, it will say a term can be a variable, a term can be one individual constant, or a term can be a function with arity j followed by a left parenthesis, then any other term, comma, any other term, j terms like this, then another right parenthesis, that is it, okay. Nothing else is a term, that is how you can express in 4 lines, is that clear. So, for example, if you write f2 1 of some x1, this is a term, right. If you say f5 0, this itself is a term. If you say f 5 1 something, so now I have to give 5 variables here, okay. So, I can take x1, I can take f5 0 as another, then I can take f1 2 of say x1 f5 0, 2 should be needed, and then I can have f5 1, okay. Then f1 0, f2 0, f1 0, f2 0, f5 0, okay. And another I can take f100 0, this is it. So, now your first job is to see that terms are really uniquely parsed, okay. You take any term unambiguously it can find out from which terms it has been obtained and how it has been obtained by using which rules in which succession, right. That is what unique parsing means, right. And you can find out whether a term is really a term or not, suggested term is really a term or not. So, like that, if you have F5 here, but only 4 arguments, then you can say that it is not a term. So, it can be parsed, only from parsing you can determine it, right. If there is no unique parsing, there will be difficulty in determining it even, fine. We will not prove again unique parsing, it will follow the same line as in propositional logic, proof of unique parsing in propositional logic. So, now we will try to formulate our original objects, which are the sentences, or how to translate the sentences into first order logic. They are called formulas instead of sentences. Even we will allow something which is not a sentence as a formula also, because to analyze a sentence we will need some in between, like you have translated one sentence, for each x, if x is a poet, then x is wise. Now, in the absence of quantifier, it is not a sentence, it looks like x is a poet, then x is wise, it is not a sentence, because x we do not know what it is, right. If you say F10 is a poet, then F10 is wise, it is a sentence, because F10 refers to one particular object, it is a constant. But if it is a variable, then a variable can take any value, it is not a sentence, right. So, as usual you are acquainted with writing in your school days, x plus y whole square equal to x square plus 2xy plus y square, it is not a sentence. You have to say what are these x and y's, you have to say for every x, for every y, which are real numbers or something, wherever it is, you have to give the scope, quantifier, how much it quantifies, or say for some x, for every y, something, some quantifier you need, then only it becomes a sentence, right. But then that unit x plus y whole square equal to so and so is meaningful, we will say them as also formulas, though they are not sentences. To analyze the sentences we will need to know its meaning also sometime. So, we will keep them as it is, we will call them also formulas, and then we have to tell which formulas are sentences, which formulas are not sentences, right. So, this is the approach we will be taking. That happens because suppose you are executing a program. So, in the program itself you are not writing what this x is, for each x, for each y, nothing is specified, right, in the program. But during the execution of the program, the variables take some particular values, they become bound by either by convention or explicitly in the program itself, right. Convention is initially if nothing is assigned, take x to be 0, depending on the languages, right. Then inside the program it can change the values, but you see always they are having some values, that is why they become meaningful, right. But before the execution, do you say that program has no meaning, no value has been assigned yet, right. So, they are just looking like formulas, they are not sentences, that is our stand. So, that means we will take in such a way approach that formulas and sentences, both of them can be taken together, and then sentences can be found out of the formulas, which are sentences, which are not, fine. So, next one is we will generate the formulas, they are also called well formed formulas, not malformed, or we just say formulas. So, we have to give a grammar for the formulas, let us write x for that, it can be top, it can be bottom, that is the first thing, okay. They can be taken as formulas itself, or they can be as pi zeros propositions, they are also allowed as formulas, right, but we take them at a time, we finish them with at a time. Well, now I remember one thing, inside the predicates you have the equality predicate also, we have missed it there. So, add it, so let us write a symbol, your usual equal symbol with straight lines, right, is being overused. So, I will use this one for the equality symbol. Then what happens, what else can be regarded as formulas. So, our generalization of the sentences which are called formulas will look like if x is a poet, or if x is a poet then x is wise, and so on. Okay. So, we start from the predicates, let us say. So, p I j, inside it what is allowed? Terms, any terms now, any definite descriptions can go, variables will be there, constants will be there, or in general any terms, right. So, there will be really j terms here, we can say t j times, or let us write t1 t2 up to tj, where t1 to tj are terms, exactly j we need. Now, if j equal to 0, then nothing is there, right. So, that itself is allowed as a formula. So, that means each proposition is also a formula, or earlier proposition in propositional logic, they are here pj zeros, they are really atomic propositions without any connectives, right. Then what else we need? Connectives we have to give. So, we will write not x, not or x and y, x or y. So, now this y we can write as x here, right, in the notation of the grammar, we do not need to write another, they can be different. Anything else? They can take quantifiers, right. So, let for is x, x, or there is x, x. This x is a variable now, any of the xi's. Okay. So, you have to say that x is any variable t1 to tj terms. Is it okay? It is simple, there is nothing much. It says that you can form formulas by taking terms as arguments in a predicate, and then use connectives, use quantifiers in the beginning, quantifiers in the beginning. But if you take quantifiers in the beginning to form first, then you can use connectives. So, quantifier need not always be appearing in the beginning, right. For example, you may say for each x 1 p 1 1 x 1, this is a sentence, this is a formula, right. It is formed correctly because 1 is there and 1 is there, this number can change depending on your context. Then you can say this implies there is x 2 p 100 1 x 2. Nothing is specified here, nothing is specified here. So, anything you can start with, right. So, for example, this is now a formula. Okay. Also, for each x 1 p 1 2 x 2 x 3, this is also a formula, right. How we give meaning we will see that later. Now, we are allowing everything, otherwise you have to really go into detail and see whether that is used or something else is used or not used and so on. That will be difficult in the grammar to see, we will take care in the when we give meaning to them. Okay. Is it clear? But if you take this as 1, it will not be a formula, right. Once you write 1, there should be only 1 argument here, not 2, right. As it is, this is also not a formula, this is the peculiarity of a grammar. We are very fussy about things now, we will not be fussy after some time. So, the thing is there still unique parsing holds, that is why we are doing it, just to prove unique parsing. We will again not prove it, because it is similar to the propositional logic, though it comes in 2 stages now, first for terms, then for this. Okay. Because it is quantifying over the variables only, it is not quantifying over the predicates. Right. For all properties something holds, no, we are not quantifying that, we are not telling that, we are telling only for all objects something happens, which are arguments inside the predicates, not over the predicate themselves. So, it is called first order. Second order logic takes care of that, where you can quantify over the predicates. For example, principle of induction, it can be properly formulated in second order logic, where you have to say for all predicates, unary predicates, this sentence, but in first order we accept it because that P becomes an predicate which is generic. So, it becomes an induction principle scheme in our axiomatic sense, it is a scheme now, put any P there, it is correct, though we are not specifically telling for every P. Once you write in that form, it becomes second order. Okay. So, we stop here. Just to summarize, we have simply presented the syntax of first order logic. Next we will come to semantics, that is what we want.